So this presentation is about notch support under LCF loading, and I would like to present here a fracture mechanics approach. First of all, I would like to outline the key idea behind this notch support interpretation. Then we will see some experimental findings, and I would like to spend some time about the novel fracture mechanics approach in order to determine these experimental findings, discussing the results and conclude the talk. So what's the key idea? We are all familiar with the local concept. What you do when you apply the local concept for assessing maybe the LCF life for a component is you put theoretically in the notch root of your component with the highest equivalent stress, for instance, a smooth specimen, and look at the experimental data of this smooth specimen, look at the crack initiation load cycles for this smooth specimen, and you say, okay, this crack initiation load cycle number is equal or is the same crack initiation life for the smooth specimen as for the component. And this is surely a very unfair comparison, because your specimen will have a homogeneous stress state, so membran loading, and your component will have a stress gradient for sure. And if you compare same equal local loading, then the comparison is unfair, because if you look at the span from 0 to a technical crack size, you will see that your component is loaded by a very much lower load compared to the specimen. And if you look at the consequence on the early crack growth up to a technical crack size, then you will see that you get a very fast crack growth speed for the specimen, but for the component, you get a comparably low crack growth speed up to technical crack size of 1 millimeter or so. So this delta M is a function of the technical crack size definition, and it is labeled here and in the paper and in this talk with notch support. It's a mechanically size effect, and it's one transferability issue between specimen and component. And what we do now is we take this early crack growth up to technical crack sizes, want to determine this by means of experiments as well as by means of fracture mechanics in order to predict this load cycle benefit for components and for various parameter combinations. Okay, let's look very roughly on the experimental findings. What we do on a 10% chromium steel at 600 centigrade, this is a turbine steel for power plant applications for rotors. We performed experiments on notched round bars, circumferentially notched round bars, and these are performed in global strain controlled. And we equipped also a potential drop measurement system in order to measure this early crack growth. And we apply also a mini extensometer in order to compare really same equal local notch root loading. This is an experimental result. You see here crack depth A over load cycles for two different specimens, one with a stress concentration factor of 1.6, the other with 2.8. Same equal local loading, same temperature without any creep effects. And you see here a load cycle difference or a difference in the early crack growth speed for the milled notch as compared to the sharp notch. So this basic mechanism is experimentally confirmed. So this potential drop measurement result are the orange circles, and you see also orange lines here. This is a load drop correlation. Due to time issues, I will not get into details about this, but we have performed a correlation by means of FEM in order to correlate the load drop which you observed in the experiment to a specific crack size. If you want to have more details, please read the paper. So, but now it would be very beneficial if we can predict this experimental findings by means of fracture mechanics, because then we can extrapolate this effect for various parameter combinations also for components. And what we do, or what we have to do, is we have to determine a crack tip parameter, so maybe a J integral or delta J, and we have to simulate plasticity-induced crack closure, because these are the two major effects if we talk about cyclically elastic plastic loading and short cracks. And we have here short cracks, so our plastic zone size is not comparably small. And the third constraint is we will not rely on any analytical solutions, because we would like to apply these concepts to components. And due to the limited application range of these analytical solutions which are available for certain standard models, this is a difficulty, and so we would choose to exclusively use the finite element method in order to simulate plasticity-induced crack closure, as well as to simulate an appropriate crack tip parameter, like delta J. But maybe we can learn from these analytical solutions. So the issue is now to determine an appropriate delta J value, so cyclically elastic plastic J integral, which is controversial, discussed in the literature, but maybe Dowling suggested to maybe put an analytical equations for J, and not only work with absolute values of stresses and strains, but with stress ranges and strain ranges, in order to get not only J, but delta J. So this is very simple, but the idea maybe is transferable also to FEM. And as an addition, if you do not work with absolute values of ranges, then you can use effective values of stress ranges or strain ranges and get delta J effective. So transferring these to FEM leads us to two approaches. One very classical orientated approach is labeled here with classical Irvine, and the other is an adjusted normal energy approach. So if we want to do this cyclic correction by means of FEM, one idea is to put directly the hysteresis branch description in the FEM. So following Masing, we work with a double Cronbach-Osgood flow law here in Abacus, for instance, and work not only with an amplitude load, but with a load range as the loading. And then we perform FEM calculations for separate crack depths, monotonic loadings from 0 up to max loading, in order to get the values of the domain integral, which are very well defined, or looking at the energy difference to get a delta J. But as I said before, what we have done so far, and what is not presented so far due to time issues, is we perform a PICC simulation, so plasticity-induced crack closure simulation, which is a very complex simulation because you have to model a transient crack row, you have to apply cyclic elastic plastic material. It's a very complex calculation. So why not using this information or these simulation results in order to get delta J? So the adjusted energy approach works with this. You have this PICC simulation, and then you do the cyclic correction afterwards. So you look at your global values of forces and displacements, and do a cyclic correction of these values in order to allow for determining the energy difference and relate the energy difference to a delta J. So maybe a few more words to the classical approach. What you can do is maybe determine the domain integral, or look at the energy difference, well-known energy difference formulation by Irvine. So you work now with force ranges and displacement ranges for a crack depth A up to a maximum displacement loading, and determine the energy under this curve, and for an A plus delta A state, look at the difference in internal energy and relate this to delta J. So very well formulated, not questionable. But if you have a PICC simulation result for a crack depth maybe of 1 millimeter, then you get a hysteresis loop, and you cannot determine an internal energy difference for two crack states without doing anything. So what you can do is you look maybe for the minimum value here at the hysteresis loop, shift your coordinate system to this point, and look only at the loading hysteresis branch in order to compare the adjusted internal energy values for two crack states, A plus delta A. And then you can relate, if you look only at the loading branch, this to delta J. Okay, let's look at the results. So this is the result for the loading branch. As I said before, we go now from the minimum value of the hysteresis loop to the maximum value. This is indicated here by the x-axis. Displacement range from 0 up to maximum. Here on the y-axis you will find the strain energy difference. And here you see a very interesting result. Maybe let's look only at the red circles. So here you see up to a certain displacement range value, the internal energy difference is 0. That's very clear because the crack is closed here up to a certain displacement range. So the energy difference has to be 0. And then the strain energy density will raise up to an end value of 0.5. The interesting thing is now we can do this evaluation not only for the loading branch, but also for the unloading branch. So if we look at these results, we see here the unloading branch going from maximum to minimum now. So 0 means maximum loading. And here you see a strain energy difference produced initially, and you observed a kink in these energy trends up to a certain displacement range. And this kink indicates the point at which the crack first closes. And the end value is also 0.5. So now we found that we determined the same effective, so-called effective strain energy differences for the loading as well as for the unloading branch. So if we look at the J integral for different crack depths for these two approaches, the adjusted energy approach looking at the unloading branch up to the kink, and for the adjusted energy approach looking for the loading branch, we see the values are absolutely identical for all crack depths. So same effective values are determined for the loading as well as for the unloading branch. You can surely look also at crack closure and compare the crack closure or this kink criterion with different criteria which are available in the literature, and you will find a very good correlation. But these are the important facts. So we have the same delta J effective for the loading and the unloading hysteresis branch, which is maybe very new. We have a new crack closure criterion identified with no inherent mesh dependency, and we could confirm the classical Irvine approach in this case. Because I forgot to mention this. You see here for the unloading branch, and this red line indicates the classical approach. You see there is a very good correlation up to the kink, up to the crack firstly closes. So this complex PICC adjusted energy approach is in a very good agreement with the classical Irvine approach, which underlines the applicability of this approach. So going back to notch support, the interesting part is determining the load cycles which are required to grow a crack from maybe 0.2 millimeters up to 1 millimeter. This is a difference between component and the specimen. This load cycle range is important for components and determines the notch support. And now with this delta J effective, which comes from the novel adjusted energy approach, we can determine the load cycles required to grow this crack. And we use a simple Paris law, and we fit this Paris law for sure with other experiments. So not directly with our notch Gompa tests, but with standard fatigue crack growth testing on CS25 specimens at the same material for sure. So and here you see the simulated notch support over the experimental notch support determined by means of potential drop measurement system. And you see these experiments as triangles for 2 different geometries and 3 different loadings, same material, take into account crack closure, and all triangles fall within a scatter band of 1.35, so a very good correlation. If you do not consider crack closure, then you get a much worse result. So crack closure is of major importance if you look at this kind of short crack growth. So I would like to conclude my talk. I will not get into details. I mentioned these points in the slides. What I would like to mention is that this approach is currently validated for this 10% chromium steel. An approach extension is under consideration for a superimposed early crack grow, and further materials are also currently under investigations. So I would like to thank the co-authors, and I would like to thank you very much for your attention. Thank you.